Okay, so let's get started. This is the second week of interactive live sessions for the course on fluid dynamics and turbomachines. This course is being offered by NPTEL. It's being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee, both from IIT Madras. My name is Debjit. I'm a PhD scholar at IIT Madras, and I'm the TA for this course. And like every other week, we shall be solving some sample problems together. So without any further ado, let's get started. So this week, there is week two. Our discussion has been on how to use integral analysis for uh, uh, understanding or describing fluid flows and associated properties. So one very crucial theorem over there that we need to even get started is the Reynolds transfer theorem. And this question is regarding that. So question number one is asking us that Reynolds transfer theorem, or also known as RTT in short, primarily provides a relationship between what? Then there are four options. So is it option A, the Lagrangian and Eulerian descriptions of fluid motion? Option B, the viscous and inviscid flow regimes or flow motion? Option C is steady and unsteady flow regimes, and option D is laminar and turbulent flow regimes. So we have, a pair of different flow regimes or flow descriptions in each option. So the Reynolds transfer theorem that connects, two of these concepts. So which one is that? Is it option A, the Lagrangian and Eulerian descriptions of fluid motion? Is it option B, viscous and inviscid flow regimes? Or is it option C, steady and unsteady flow regimes? Or is it option D, laminar and turbulent flow regimes? It's a simple one to start with. Um, let's take a look at the solution. It's actually option A, the Lagrangian and Eulerian descriptions of fluid motion. That's the correct answer. So basically, uh, all most of our conservation laws, we know them for a control mass or a system approach. We know them from a system or a control mass approach. So what that tells us is that, there is a system or a control mass, which is like a fixed amount of material of, let's say, some mass m. It's a closed system, meaning that through its boundaries, no new mass can come in or go out. It's a identified uh, volume or unidentified quantity of mass, and all our laws basically starting from Newton's laws of motion or conservation of energy coming from the laws of thermodynamics. uh, all these laws are known for a control mass or a control system, uh, or a system viewpoint. But what happens in fluid motion is that it's very difficult to follow such a mass. So let's say I have a pipe like this with some fluid going flowing through it. So it's very difficult to identify a packet of fluid and then follow it, because as it turns out that fluids deform and stretch and they rotate as it flows. So this might transform into some weird shape like this and keep deforming and do things. So it's very difficult to apply the control mass system, or this whole approach is known as the Lagrangian frame of reference or Lagrangian description of motion, where we sit on a block of mass and follow that mass. But as it turns out, it's difficult to apply in case of a fluid flow. So here what we do, we fix a sort of a window or a volume we fix in space and try to focus over there. So in a 2D, it's like, you have a camera and you're focusing only on a small finite-sized frame. So in that frame, new atoms or compounds of fluid can come in and it can flow out, and along with the fluid there could be it could carry in energy, it could carry energy out, it could carry in momentum, carry momentum out. Also it can carry properties in and out. So in order to apply the laws of physics that we know, like Newton's laws of motion or laws of thermodynamics, we need to transform this all those laws from the Lagrangian frame of reference to an Eulerian frame of reference, which is this, where we do not follow any fixed mass, but rather we focus on a fixed volume, which is also known as control volume or CV in short. So RTT, what it does is that it provides a relationship between this Lagrangian frame of reference with the Eulerian frame of reference. And as we have seen for any general property B, if we divide that per unit mass and get some intensive property beta, then in that case we can write something like this: d beta dt for a system is equal to dou beta dou t, or rather I shouldn't write beta but dB, and here it should be rho beta. So this is, and this has to be integrated within the control volume. So I write V cross. So dV cross is, some elemental control volume. And if you integrate it over the whole control volume, so this integration is over the whole control volume. So you get whatever property is changing with respect to time within that control volume. But that's not all, because new mass is coming in and mass is flowing out, and that mass carries the property beta along with it. So we get another additional term, which is given by this rho beta multiplied by the flux, which is velocity v vector into dotted with an elemental surface area. So once again, ds is, so I'll just define these things. So let's say if I have a control volume PV like this, my control surface is this, the CS, and one elemental volume within this control volume is this dV. Now V with a cut represents volume, strike, with a strike through, and capital B V vector is the velocity. So coming back here, so this is integrated over the control surface, and once again, some elemental portion of the control surface, that's ds, and it is a vector with the direction out from the control volume. So yeah, so this is what the Reynolds transport theorem does, and it lets us connect the Lagrangian frame of reference, which is in the left-hand side. This is the Lagrangian frame of reference with the Eulerian frame of reference on the right-hand side. Right. So that was question one of today's session. Let's move on. We'll move on to question number two, which is asking us which of the following conservation laws can be derived using the Reynolds transport theorem. So week two has been on the application of different integral analysis of fluid flow to analyze flow dynamic systems. And one important theorem over there is this Reynolds transport theorem, which lets us connect the Eulerian frame of reference with the Lagrangian frame of reference. And this particular question is asking us which of the following conservation laws can be derived using the Reynolds transport theorem. Is it option A, only conservation of mass? Is it option B, only conservation of energy? Is it option C, only conservation of angular momentum? Or is it option D, all of the above? Read the question carefully, and it's a simple one. And once you've figured out the solution, you can either unmute and answer, or you can type in the chat box, however you feel comfortable. So this is question number 2 for the second week of interactive live sessions for the course on fluid dynamics and turbomachinery. And this is our so this question is asking us which of the following conservation laws can be derived using the Reynolds transport theorem? Is it option A, only conservation of mass? Is it option B, only conservation of energy? Is it option C, only conservation of angular momentum? Or is it option D, all of the above? Okay, so let's take a quick look at the solution. It's actually option D, all of the above. So what Reynolds transport theorem tells us is that for any extensive property B, we can define, the per unit mass version of it or the intensive property version of it, which is that property B divided by mass M. And Reynolds transfer theorem then can be written as the time rate of change of B of that system is equal to the integral over or sorry, the dou t, the time derivative of the integral of rho beta into dv, where this stricken through v is the volume, and this has to be integrated over the control volume plus the integral of again rho beta into velocity vector v dot ds, which is the elemental control surface, and this has to be integrated over the control surface, the entire control surface. So given this is my control volume CV, this surface surrounding it is the control surface. So this is what Reynolds transfer theorem tells us. Now, this property that we are, uh, you know, trying to study can be anything, any extensive property. So it could be mass. So if replace B with M, then our beta becomes 1. Then, you know, plugging these in into the Reynolds general form of the Reynolds transfer theorem, we can recover the continuity equation. And that helps us conserve mass in case of any fluid flow. Similarly, if I replace V with momentum, that is mv. So uh, again, this can be a B, the property B can be a scalar, it can be a vector as well. So beta then becomes velocity v, and plugging this in would give me the conservation of linear momentum. Similarly, yeah, I can replace this with half mv squared, which is the kinetic energy, in which case beta would simply be half v squared. This would give me conservation of energy. And this is only kinetic energy. You can add internal energy over here, and then you'll be able to account for heat energy as well. Then this just follows. So I can do angular momentum as well. So I'll just do r vector cross mv, which is my angular momentum. In that case, beta would become r cross v. And again, I can replace this, I can plug that into the general form of the Reynolds transport theorem, and then recover a conservation law for angular momentum for any given fluid flow. So that is why none of these options which say that it's only conservation of mass or only energy or only angular momentum are wrong. Rather, all of the above can be derived using the Reynolds transport theorem. Any questions on this or anything else? These are supposed to be interactive sessions. So, if you have anything on your mind, please do not hesitate to speak up or type in the chat box. Anyway. All right. So, hope this was clear. We will keep moving. We will move on to question number 3 now, which is asking us that in case of a firefighter holding a high-speed water hose, which property can be calculated using Reynolds transfer theorem with linear momentum as the extensive property? So I'll try to draw a very bad sketch to show what I mean. So let's say there's a firefighter and the firefighter is holding a water hose like this, and there's a building on fire over here. Right? And the firefighter is trying to extinguish this fire by uh, pouring some, by directing some high-speed water jet towards that fire. So in this case, if I, take linear momentum as my extensive property and plug that into the Reynolds transport theorem, then what quantity will I be able to calculate? Is it option A, the total mass of water in the hose? Is it option B, the force exerted by the water on the firefighter? Is it option C, the increase in temperature of the water? Or is it option D, the air pressure surrounding the water jet? Which one will it be? You can unmute and answer, or you can type in the chat box as well. At least do try to respond, Even if you're not sure, you can take a guess. Like giving a wrong answer here doesn't really matter. So this is the question that in case of a firefighter holding a high-speed water hose, which property can be calculated using Reynolds transfer theorem with linear momentum as the extensive property? Is it option A, the total mass of water in the hose? Is it option B, the force exerted by the water on the firefighter? Is it option C, the increase in temperature of the water? Or is it option D, the air pressure surrounding the jet? What do you think? What could it be? Any guesses? Okay, let's take a look at the solution. It's actually option B, the force exerted by the water on the firefighter. So I'll just go back to my beautiful schematic over here. So the thing is that if I want to calculate the total mass of water, uh, applying RTT doesn't really make sense. I can just, find out the total volume of the water hose and then multiply it with the density of water. Or, if it's varying, I can do an integral and all sorts of things. But for that, Reynolds transfer theorem is not really required. Now, in the second case, the force exerted by the water on the firefighter, that's exactly what I'll get if I, you know, draw a control volume around this nozzle, and that would give me what momentum efflux is coming out of the control volume and what is going into the control volume. And the difference of that should give me the force exerted by the water on the firefighter. Now, in order to hold it steady, the firefighter has to apply, an equal and opposite force to hold it steady. And that amount of force can be calculated by using, linear momentum conservation, uh, which can be derived using RTT. Now, the other two options, the increase in temperature of the water. In order to find this, so temperature of the water is related to the heat energy of the water. And in that case, it's not linear momentum, but rather energy, kinetic plus heat energy has to be considered as the extensive property. So that can be done using RTT only, but then we need to conserve energy, not linear momentum. And the final one for air pressure surrounding the jet, this is a bit more tricky one. So maybe integral analysis may not be enough to answer this question. But however, for this particular situation, the air jet has come out into the open atmosphere, and the pressure everywhere would be equal to the atmospheric pressure only. But in any other case, we need to uh, explicitly solve for the flow fields to get the pressure distribution. So that would require a more in-depth differential analysis, and integral analysis may not be enough to answer this question. So, coming back to the question at hand, so if we do conserve linear momentum, we would be able to compute the force exerted by the water on the firefighter. Okay. Any questions on this? Questions, doubts, remarks, comments, anything? Okay, hope this was clear. We shall then keep moving on. We'll move on to question number 4, which takes question 3 and asks us to do exactly what we predicted. So it says that a firefighter is holding a water hose that expels water at a high velocity V to extinguish a fire. The diameter of the hose nozzle is d, the density of water is rho, the hose is perfectly horizontal, and the water exits in a jet directed straight ahead. Now, this may be a little bit incomplete. So let's say my nozzle is like this. This exit diameter, let's call it small d, and water is coming out with a high velocity v. And similarly, so if this is what we consider to be our control volume, then there has to be some fluid flowing in from here as well, the fluid being water over here. So let's say this velocity is capital U, and you know this is at some larger diameter, capital D. In this case, we need to find out the force exerted by the firefighter on the hose. So as I said, the water momentum might be greater, and the efflux of momentum of the water through the nozzle might be greater, and you know it would exert some force on the firefighter. The firefighter has to apply an equal and opposite force in order to hold it steady. That force has to be computed. So let's take a look. So let's use a simplified version of uh, the RTT for linear momentum. So I'll just start with the general form. So the general form says that the rate of change of momentum of the whole system should be equal to the time rate of change of momentum within the control volume plus the net efflux. Control surface, integral over control surface. I have my properties here, and this is the efflux, right? So let's simplify this down a bit. So since it is steady, this term goes to zero, and this term over here. Now we don't really need to integrate since the velocity u is constant over this whole surface area as well as the velocity v is constant over this whole surface area, and there's no flow going out the walls. So we can simplify this second term into a summation. So we can say that, you know, let's call this surface 1, let's call this surface 2. So whatever rho v v into, and let's say I know this area, so let's call this A1 and A2. This into A1 and all of this at 1. This will be negative since the direction of velocity and the surface area are opposite to each other, and at 2 will be plus. Let's forget these things for now. Let's make them scalar quantities since we know that the direction is in the x direction only. This will be 2. And from Newton's laws of motion, we know that the rate of change of momentum should be equal to the external force, the sum of all external forces applied on the body. So this is what we're trying to find. So let's replace these things. So this will be minus rho for 1, it will be capital U squared, and A1, that is the area of the inlet, that is pi capital D squared by 4. And same thing for the outlet. So in this case, it will be small v squared into pi small d squared by 4. This difference, which can be written in a bit better way like this, we call this v squared b squared minus u squared capital D squared. And this is equal to the external force applied on it. The only external force applied on this is by the firefighter. So that's the force which we're looking for, and this should be the answer. Now, there's another thing which we didn't consider in the while considering the external forces, that is the pressure. So on this surface, surface number 2, it's coming out in the atmospheric pressure. So we know it's just PATM, or we can ignore this as well. So considering only gauge pressure, this would be 0. Whereas, sorry, on the other side, that is the fluid which is still within the pipe, that could be at a higher pressure because there's some pump upstream which is pumping this fluid, right? And ensuring continuous high-speed flow of water. So there could be a pressure distribution over here as well, P1. So in that case, this has to be considered on the left-hand side along with the external forces, and so this would be plus some P into A1, which we know is pi d squared by 4. And if you need to find F in that case, then you need to subtract it from the right-hand side. So in that case, the force that we're looking for F would be equal to pi by 4 rho this difference v squared d squared minus u squared d squared minus P1 A1, let's call it P1, which is the pressure on the inlet side of the nozzle. So that pressure would actually help the firefighter. You know, firefighter would have to exert a lower amount of force to hold the hose steady. Right? Any questions on this? Am I audible, by the way? Sorry, I didn't check earlier. Am I audible and is my screen visible? Anyway, I'm not getting any responses. So I hope things are fine and I'll carry on. But please do let me know if there are any problems. All right. So hoping this was clear, we will move along. We'll move on to question number 5, which is a simple application of mass conservation equation. So it's telling us that consider a steady flow in a water pipe joint. So uh, there is this three pipes connected at a joint, and there are flows coming in and going out to all sorts of things. So from one, there is fluid coming in. From three, there is going out. From two, what happens, we don't know. We need to find that out. And there is a leakage at four. So fluid is flowing out of that. So we can consider that as another outlet as well. So the areas are given A1, A2, A3, and the whole volume flow rate out of 4 is also given. So let's call this Q4, which is given as zero point 0.1 in SI units. And the velocities at 1 and 3 are also given. So I know what V1 and A1 is. I know what V3 and A3 are. I know what A2 is. I need to find out what V2 would be. So, considering that this is a steady flow and applying Reynolds transport theorem for mass conservation. And we won't do the whole integration now since we know that there are discrete surfaces through which the flow occurs. So we can convert that into a summation. So we can just say summation of all the uh, mass fluxes should be equal to zero. And mass fluxes are basically density into uh, flow rates. So any mass flux is equal to rho into qi, I being the index going from 1, 2, 3, 4. And we can ignore rho for a while as well, considering that it's an incompressible flow. So, it would ultimately boil down to summation of all qi. So I'll call this I, summation over I. Summation over I should give me 0. And okay. So now let's just break it down into all of these components. So first of all, V1 A1 plus V2 A2 plus V3 A3. And we already know what V4 A4 as a composite, as a product is. So I'll just call that Q4 is equal to 0. And we know all these values, so it's a just have to do a simple sum. So V1 is 5 meters per second, A1 is zero point 0.2, V2 is something that we have to find out, A2 is something that we know, so I'll just call that zero point 0.2 into V2, then V3, A3, V3 is 12. Okay, so here it's interesting. So V3 and A3 are in the opposite direction, right? Sorry, V3 and A3 are in the positive direction, so that should be plus, but V1, A1 is negative because that's flow coming in and our area is pointing outwards. So this has to be negative. V3 is okay. So we will assume that V2 is also going outwards. If it turns out to be negative, then that means that, the flow goes in. But, let the math dictate that. And V3, A3 is again positive, so that's 12 into A3, that is 0.15. And Q4 is also leakage that is going out. So that's point 0.1 is equal to 0. Let's compute this. So the first one is -1 plus zero point 0.2 V2 plus 12 into 0.15. How much is that? 12 15s are 120. No, sorry. Fif- 50, 180. And it's 0.15. So 1.8. 1.8 plus zero point 0.1 should give me 0. So this is minus 1.8 plus, okay. So V2 is equal to minus zero point 0.9 divided by zero point 0.2. So that's minus 4.5 meters per second. Now see, we assume that V2 is going outwards, but since the value is negative, it's actually flowing inwards with a velocity of 4.5 meters per second. Simple enough. Any questions on this? Okay. If not, let's move along. Move on to question number 6 now. In question number 5, we saw a simple, example of the application of Reynolds transfer theorem for mass conservation in any given system. Now, in question 6, we will learn how to apply linear momentum conservation in order to find the force. We saw a similar example for the firefighter example as well. This is another one, then this is a little bit more tricky. So as you can see in figure 1, water enters a two-dimensional channel of constant width h. So where is my cursor? So this is the inlet where an uniform flow of velocity u enters, and it's of constant width h, and it takes a bend. The flow takes a bend like this, and then leaves out with a velocity profile like this. It's a linear velocity profile. It's given in the question. So it's V max is the maximum one towards the inner end of the curvature, and V min is the minimum velocity towards the outer end of this curvature. And inside, it's like linear. So, V being the velocity at any point, and since our coordinate system is here, our origin is here, so V can be written as V max. It linearly goes down to V min, so this will be you know, negative of V max minus V min. My width is still h, and it's a linear function of x. So it linearly reduces down to V min. You can check that. So if you put x equal to h, these two would cancel out, V max would cancel out, and I'll get V min. All right, so that's the velocity profile, and it said that there's a inlet gauge pressure of P as well. So there's the pressure P over here, and the outlet is at atmospheric pressure. So the gauge pressure would be 0. So you have to find out the force required to hold the bend in place. Now, how do you do that? You simply apply conservation of linear momentum, and there are only two surfaces that you have to consider. So uh, should be pretty simple. But to start with, we know what the value of u is. We don't really know what these values of V max or V min are. So those values can be found out in terms of U using the conservation of mass. So basically, as we did earlier, so rho I'll take outside. So let's just write it this way. So the summation of the mass fluxes would be equal to zero. So mass flux in minus mass flux out should be equal to zero. Mass flux in is nothing but U into H, and if you consider a span of one, so per unit depth of this, so I'll just write one over here, which is one is the in the z direction, what is the distance, minus whatever goes out. Now whatever goes out has to be integrated since it's a linear velocity profile over there. So that integration would be something like this. So that integration would be from x equal to 0 to h, and okay, there's a row outside over here. We will ignore that and just consider volume flow rates. So this would be v dot dx dot 1, which is along the depth. So that gives me the velocity flux outwards. So that would be 0. Now let's try to do the integral now. So 0 to h. V we wrote over here. So that would be V max minus V max minus V min divided by H into X integrated over dx equals 0. Now let's do the integration. So it's V max integrated would give me X, and H to 0 would give me H. Then this negative and this negative would cancel out each other and give me plus. So I'll have V max minus V min divided by h into x squared by 2, and plugging in the values, I'll get h squared by 2 equals 0. Right. So another relation that we know, which is given in the question, is that V max is equal to 2 V min. So let's call this equation 1, and equation 2 is that V max is equal to 2 V min. By solving these two, I can find out Vmax and Vmin in terms of U. So let's do that quickly. So I have UH minus Vmax. So I'll just replace Vmax with 2 Vmin right now. Sorry. 2 Vmin into H plus, okay, Vmax minus Vmin should give me another Vmin divided by H multiplied by H squared by 2 equals 0. So one H would cancel out here, and I can cancel out another H all throughout. So nothing really stays. So I get over here minus 2 Vmin plus Vmin. So let's take these two things on the right hand side and flip the order. So that should give me 2 minus half. That is 3 halves. Vmin is equal to U. Vmin is 2U by 3, and Vmax is twice that. So it should be 4U by 3. Now we know these two values in terms of U. So the first part is out. Now the second part is doing the momentum conservation. So I'll use a blank slide over here to do that. So basically just to draw our problem, once again, I had a linear velocity profile like this and a uniform velocity profile like this. I need to find out what the forces are. So forces can be in two directions, right? It can be in x as well as y direction. So we need to solve them both separately. So the first one would be, Fx, that is the force applied by the external uh, body. So there could be, some support to this bend which has to be given. So that would give some reaction force holding this whole pipe together. So that force Fx, uh, there's an so there's P into this area as well, because if you remember there was some gauge pressure P, so that's part of the external force into the area which is small h. This should be equal to the net difference between the linear momentums coming in and going out. So momentum going out has to be integrated. That is rho v square into dx. X goes from 0 to h, and whatever comes in is simply rho u square into small h. Now let's evaluate this integral. So I'll take the rho outside, 0 to h, and the formula for V was, again, the formula for V was V max minus V max minus V min by h into x. So I'll keep, although we know what V max and V min are in terms of U, let's keep them as it is right now for mathematical simplicity. And you have to take the square of this. So I'll get V max squared plus V max minus V min over h squared into x squared minus 2 V max into V max minus V min by h into x. So this whole thing, and there's dx on the outside and minus rho u square h over here. So rho, then let's do the integral. So the first term is V max squared into x, and that would give me h plus rho. This is just a constant. Integrating x squared would give me x cubed by 3, and plugging in values, I'll get h cubed by 3 minus 2 v max minus v min by h and x. So x squared by 2, that will be h squared by 2 minus rho u square h. So it's all algebra at this point. So you can simplify this. So let's take rho and h common. That will give me v max squared. So I'll just take a quick look. V max is 4u by 3. So that's the square of that. So 16u squared by 9. Plus v max minus v min is v min squared. And v min is 2u by 3. So that's 4u squared by 9 minus 2. V max is 4u by 3, and this should give me V min, which is 2u by 3, and there's another half over here, and there's u squared over here. So now we can take u squared out as well, which leaves us with 16 by 9 plus 4 by 9. 2 cancels out, that gives me minus 8 by 9 minus 1. It's just a lot of algebra at this point. 16 plus 4 is 20. 20 minus 8 is 12. And 12 minus 9 is 3. So 3 by 9, that's 1/3. So this should be equal to the Fx is this minus pH. Ah, sorry, I've made a mistake. So while considering the x momentum, this really doesn't come into the picture, right? Because that's going out the y direction. So it should be just, sorry. Anyway, this integration should be helpful in finding Fy. So basically, this is correct what I'm doing right now. Whatever I did earlier was wrong. So this should be equal to minus rho u square h, and that's it. There's no x momentum going out the outlet. So my Fx should just be minus pH minus rho u square h. That's the force in the x direction that's required from the outside. And for Fy, it would be just this integral over here because there's no y momentum coming in through the inlet. Right. So this should give us not this part, but the remaining one. So 12 by 9, that is 4 by 3. So 4 by 3 rho u square h. This should be the y direction force. And if you are interested in the total magnitude of force, then you can just take a square root of the sum of these two forces. So sorry, I made some mistakes earlier. These are wrong. This is the correct one. Any questions on this? Sorry, I messed up a little bit initially. Is the concept clear? Like, there's only x momentum coming in through the inlet, so that's the only thing we consider while computing the x direction force. And for the y direction force, the inlet doesn't matter, it's only the outlet that matters. So that gives us this particular value. Okay, hopefully that's clear. We'll keep moving. So this is the last problem of today's session. It's a classical problem. So it's called the sprinkler problem. So it's a very crucial problem for demonstrating the conservation of angular momentum. So this is our sprinkler. So if we take a top view out of it, so there's some velocity going out, sorry. So there's some velocity going out this way, there's some flow going out with a velocity this way, and sorry. So that would, push this sprinkler back, right, when it's going out. So that would cause a torque, causing this whole sprinkler to rotate. And to balance out this torque, a frictional there's some friction in the bearing holding the sprinkler, which, as you can see in the question, is given as k omega, omega being the angular rate of rotation. So this is k omega. And when these two torques balance out, it causes a steady rate of rotation. There is no acceleration or deceleration as such. So in this question, we are given what the volume flow rate Q is. So there's a volume flow rate coming in. We know the area of the outlet of the nozzles. So Q divided by that area, Q by 2, since it splits into two nozzles. So that should give us the velocity, and we know the angle theta as well. So and this angle, this particular angle would be 90 degree minus theta, pi by 2 minus theta. And this moment arm is the same as the radius of the sprinkler, which is capital R. And this information should be enough for us to find out what the steady state angular velocity omega is. Okay, so let's get started. So we'll start off by once again using the Reynolds transport theorem of now this time for conserving angular momentum. So instead of forces being on the left hand side, now it should be the sum of all external torques, and that should be equal to whatever angular momentum is coming out minus whatever angular momentum is going in. Now you can see that the flow is basically perpendicular to the plane in which the sprinkler is. So there's no angular momentum coming in. There's only angular momentum going out. And the only external torque applied here is this frictional torque, K omega. So I'll shift here for more space. So the external torque tau is K omega, and that should be equal to the linear momentum going out, which is nothing but twice of the linear momentum. So no need of integral here. We'll just do r comma. So there'll be a rho I'll take outside. There'll be a r cross v into the area. Sorry, this is the momentum, and that should be multiplied by the area. That's correct. But yeah, anyway. So the velocity, the magnitude of velocity, as we saw here, is Q by 2A, if A is the area of the nozzle. Q by 2 because Q splits up into two arms of the sprinkler. And while doing R cross V, so coming in here, K omega equals to rho R cross V, so that would be R into this velocity V multiplied by sine of pi by 2 minus theta, which is cos theta, by the way. We will replace that soon. And there's another V over here, so V squared, and there's A. We'll write that A. It should again be equal to R V squared. Let's replace the magnitude of V now. So it should be Q squared by 4 into A squared sine of pi by 2 minus theta. As I said, is cos theta. And there's an A over here. So there's an A over here. So this A and this A would cancel out. And finally, we can get omega as 2 rho r q squared by 4 k a into cos theta. This would be the steady state of the steady state angular velocity, which balances out the external flow of momentum with the uh, frictional torque applied by the bearing on the sprinkler. So this is a classic problem for learning how to apply the concepts of angular momentum conservation for flow. Now, There's an interesting, you know, segue from here, which is known as the Feynman's sprinkler, which sort of proposes an opposite scenario of this. So let's say, uh, I dip the sprinkler into a fluid, into a whole bath of fluid. So let's say, if this is water flowing out, then let's say I dip this whole sprinkler inside a bath of water. And then this part, this Q is connected uh, to some pump which sucks out fluid right now. And so earlier it was a flow going into the sprinkler. Now let's say I have some mechanism to suck out fluid from here. So in that case, fluid would rush in from the outside to inside the sprinkler, right? So intuitively, you might think that the sprinkler would now rotate, it should rotate in the opposite direction, right? But that's not the case in reality. What happens is something much more complicated. So yeah, so there could be multiple scenarios. One is the whole direction of rotation could get reversed. That's one way of thinking. Another way of thinking is that since flow is coming in and let's say hitting it over here, it should cause the sprinkler to still rotate in the same direction it was rotating earlier, right? So that's another way of thinking. But in reality, none of those are realizable. Actually, what happens is most of the energy is lost due to viscous dissipation, and the sprinkler barely rotates. So that's the Feynman sprinkler. And recently, there has been some experiments with using very slow flows and very controlled experiments which reduce the friction to a very low extent. They showed that it is indeed possible to rotate the sprinkler in the opposite direction when reversing the direction of flow. So it's a very interesting topic. You can uh, search on this and spend some time on it. Okay. Anyway, so that's all for questions from my side. If you have anything, please ask away. Otherwise, we will, meet again next week, same time from 3 to 5. Okay, then. So if you don't have any questions, let's end this.